How is everybody? Did you get your coffee? Good. Any questions so far from the material that we've covered? Okay, so let me do a quick review as usual. So what we covered yesterday was applications of sequences. We basically showed you this cool interface on sequences that allows you to do a bunch of the operations, also operations in parallel. And then we talked about applications of this to two problems: maximum contiguous subsequence sum, which we called MCSS, and breadth first search on graphs. And basically in the case of MCSS, what we did was we covered different algorithms, one based on scans and one based on divide and conquer. And for both, we achieved order n work or log n span, and this is basically optimal. Okay, it's a classic problem. And in fact, our divide and conquer algorithm is basically the same divide and conquer algorithm that was used in sequential setting, except that we could do the two branches in parallel. And that gives us the optimal span. So the lesson from this is that the carry away is that, well, you don't need to be sequential to solve this problem. You don't have to sequentialize your computation. You can achieve log span without much difficulty. Now, BFS on graphs, basically same story, right? So there, the problem was to traverse a graph layer by layer, starting from a source. And the algorithm basically maintains, all it does is it maintains a frontier set, which is initially the source, and then visits everything in the frontier in one swoop, so in constant span, and proceeds to the next frontier and so on. And therefore, the span is order diameter of the graph. Now for work, the key, there's really not much complication here. The only difficulty is that once you're in this frontier, let's say you're here, and then you want to compute the frontier for the next step, what you want to do is take the out edges of the existing frontier, find where these vertices that are reachable, and then make that be your frontier. Except, this is obviously very easy, except that you have possibly conflicts. So these two guys might both point to this vertex, and you then will have duplicates if you do a straightforward map. So you would get A, B, B, C, but you want your frontier to be A, B, C, not A, B, B, C. So you need to do duplicate elimination. Now you can do duplicate elimination purely functionally. That'll cost you a log n in terms of the work and span. Or you can use our inject function, right, on single-threaded sequences, and that gives you linear work. And with that, we get order n work instead of order n log n work, basically. Now, what's cool is that with the new single-threaded interface, it is still consistent with purely functional programming, right? But because you never access older versions of data, you don't pay for it. So you get linear work and diameter span. Again, both of these are, so far as we know, quote-unquote optimal. It seems unlikely, as Guy pointed out, that we would be able to do breadth first search in less than diameter span. Okay, any questions? Yeah, Guy?
I said that there was an extra log n in the span for each layer of the filter and stuff.
Ah, right, yeah, sorry, good. We tend to forget the log n factors. Yeah, that's right. So in each layer, this inject is going to cost us log m span, I believe, right? Where the m is the number of things that are being injected. That's bounded by n, so you get that. Yep. Excellent. I see I'm being sloppy again about something here. This should be, you cross each vertex, each edge once, so it should be really m in terms of the number of edges. Okay. Good. Questions? Okay, so that's and now BFS is one of the simpler algorithms. You can parallelize many other graph algorithms, and you can read more about that in our notes. That we're not going to go into that anymore. But there is a technique called contraction. There's an adaptation of the contraction techniques for graphs. It's a bit more sophisticated than just doing contraction on sequences, which is what we did for scan to implement scan efficiently. But the contraction technique on graphs basically gives you a way of operating in graphs in log n rounds. And you can solve connectivity, for example, parallel connectivity using that. Minimum spanning trees can be parallelized using that technique. So it's a powerful technique, and it gives you good parallel algorithms for a whole range of problems on graphs. Again, we won't go into that, but you're more than welcome to read it in our notes. Okay, today what we want to move on to is another fundamental data structure. So the past few days was sequences, fundamental data structure, and applications, and basically we are moving on to increase our vocabulary, binary search trees, right? Or you can think of them as sets and dictionaries. Another fundamental data structure, right, for implementing sets and dictionaries. And we're basically going to show you that much like in sequences, in fact, binary search trees accept a very similar treatment. You can get work efficient but fully parallel operations on binary search trees and implement, therefore, sets and dictionaries reasonably efficiently. Okay? So, what are binary search trees? Who knows about binary search trees? Anyone who doesn't, a reminder, a very quick reminder. What's a binary search tree? It's a full tree, right? Where each node has either two children. Each node is either an internal node or a leaf. Leaves are drawn as boxes here. And each node has a key. So you could have keys like this. So you can have keys like this on the internal nodes. That's the general structure. So we can write the ML data type for it as follows. Data type. Let's not worry about the type of the keys right now. Well, I guess we could do alpha tree. It's either a node with two trees, left tree, a key, which is alpha, and the right tree. So that's called the left subtree, that's called the right subtree, or it's a leaf of nothing, right? So this subtree is called left subtree, that subtree is called the right subtree for each node. And the key property here is that the key at any vertex, any node, is greater than the key on its left and less than the key on its right. Okay, so for example, 8 is greater than 5 and less than 10, and this applies to all the nodes. Inductively, that means that this vertex, this node here, the key at the root, is greater than all of the ones on the left and less than all of the ones on the right. So that's the key property. Now traditionally, right, you have, in sequential computing, you're interested traditionally on basically just a few operations on binary search trees: find, insert, and delete. Okay, find takes a key and a tree. So it takes an alpha and an alpha tree and returns a bool indicating whether that key is in the tree or not. Insert takes an alpha and a tree and returns a new tree that has the key in it. And delete takes an alpha and an alpha tree and then gives you a new tree that does not contain the key. For example, if you want to insert 7 into this tree, okay, we have no other choice but insert it here. Okay, assuming that we don't do any structural changes, this is where we would insert further rebalancing. That's where we would insert the key 7, because that's the only place that fits. We can implement a find by following a path. If I'm looking for the key 12, I go to 8, and 12 is greater than 8. Therefore, I know I need to go to the right, because all of this stuff here is less than 8, and so on. And I find, if I reach a leaf node, before I find the key, I know that it's not there. If I'm looking for the key 9, I follow this path, and I know it's there. So these operations can all be implemented reasonably efficiently by just following paths, and therefore, if the tree is kept balanced, if we make sure that all leaves are approximately at the same level, that would be efficient and logarithmic work. Now, as in sequences, right, these operations are not sufficient in parallel computing. We actually need bulk versions of these operations, meaning that these basically allow you to do one thing at a time, one find, one insert, one delete. What you want to be able to do often in parallel algorithm is do a bunch of finds at the same time, do a bunch of inserts, bunch of deletes, okay? So we need basically bulk versions of these operations. And what are they? So the bulk version of find can be thought as an intersection operation. Okay, intersection operation takes 2 trees, and then gives me another tree that consists of the keys that are shared in these 2 trees. As the name suggests, you can think of that as set intersection. So it intersects the keys in here, and it gives you a binary search tree that actually consists of only the keys in both. Okay? So that's a generalization of find. Now insert, you can imagine, right, is the union operation. So if you have 2 alpha trees, and you have a tree and you want to insert a bunch of new keys, well, you make a tree out of them, and then you call union to get a new tree that contains the keys in both trees. And delete is, we call it difference. You can think of the set difference. These are, by the way, as you probably figured, these are inspired, the names are inspired by set theory, in mathematics. So difference would be, you're given a tree, and then you take another tree, and you return another tree that consists of the keys that are in here, but not in here. Okay, so let's specify perhaps a bit more carefully. So if this is, let's say T1 and T2, symmetrically for all of these operations, this operation gives me a tree whose keys consists of the keys of T1 and keys of T2. That operation gives me keys of T1 and keys of T2. And this operation gives me keys of T1 set minus keys of T2. Okay? Is it clear why these are bulk versions of find, insert, and delete? Make sense? Okay. So now, once you have these operations, you basically have full binary search tree experience in parallel, right? You can do operations like this one by one, or you can do operations like this in bulk. Cool. Now, question is, how do we design a data structure that supports these bulk operations, right? So what we want to do is design a data structure that supports these operations in a work efficient and low span fashion. Okay, good. It turns out that basically, going back to the sequential binary search trees, the key technique to make them work what's the key technique that make them work efficiently? What do I need to do, for example, if I want to make sure that insert, delete, and find operations all operate in log n time or work in the sequential realm? Balancing, right? Yeah, balancing, exactly. Good. Now, how do you balance things? Well, it turns out there are many ways of balancing, right? You can use splay trees. For example, they use a particular balancing technique. You can use red-black trees. Okay, it's a bichromatic tree, so it uses colors to balance. There are I think the very first data structure was AVL trees. AVL trees use balancing, very elegant way to balance. There are weight balance trees, also very cool data structure, incredibly flexible, also very good for implementing sequences, actually, weight balance trees in an efficient way. You can implement sequences, all of the stuff that we talked about based on arrays using weight balance trees. Elegant, you get elegant solutions and reasonably fast performance. So these are all techniques that I'm sure there are a bunch of others that I'm missing, but these are some of the main techniques that's been used to balance data structures. Oh, and I shouldn't forget trees. These are probabilistically balanced trees. They are incredibly they're incredibly clever, right? And also very efficient, very simple, very elegant data structures. They have, in some ways, there might be the simplest data structure of all of these to implement. Actually, we will see how we can use trees, for example, to implement these operations. Okay, so these are some of the. How many of you know trees? Raise of hands. Oh, okay, not many of you. Good. So we'll cover that. Now it turns out all of these use different balancing criteria, balancing techniques, and basically we can implement all of these operations, intersection, union, difference, by effectively borrowing the balancing ideas from these trees and adapting them to support these operations. Okay, and in this lecture, we're going to see just one particular way of doing that has the advantage of basically localizing all of the balancing into two operations. So that you can plug and play, you can basically take these operations and implement them using different balancing techniques, and you'll get implementations of this interface. So these two operations are split and join. Okay? In order to implement these operations, what we're going to do is imagine or implement two operations called split and join for trees that basically will allow us to implement all of them in terms of this, and all of the balancing operations will basically be focused on these two. In fact, not even split, but just join. Okay. So what does split do? It takes a tree, alpha tree, and it takes an alpha, a key, and then it returns us a Boolean indicating whether that key is in the tree or not. And then it also returns two trees such that all of the keys in the left is less than alpha, and all the keys on the right are greater than alpha. Okay, let's see an example immediately. Suppose that I have that tree there, and let's say that I split that at, pick a number, 5. Okay, so what we'll get is true, because 5 is in that binary search tree. And then 2 binary search trees consisting of the keys 3, 4, okay, because these are less than 5, and all the rest. What is what? 6, 7, 8, 9, 10, 11. Okay, because these are greater than 5. Okay, and then we get a true indicating that 5 is in there. Now, in general, right, we don't care about how these 2 trees are structured, but that will be determined exactly what balancing technique we use. Exactly, what tree you get there, what tree you get there. We don't care exactly how they look. Split only specifies that the tree on the left contains things that are less. The tree on the right contains things that are greater. That's all we care about it. Okay? And join is, you can think of it as the dual of split. It takes 2 alpha trees such that the keys on the left are all less than the keys on the right, and it gives us a new tree that contains both. It's not union exactly, right? Because it has the requirement that the keys on the left are all less than the keys on the right. So you could, for example, have a binary search tree like this, 3, 4, and a binary search tree like this, 8, 6, 7, 10, 9, 11, okay? You can join these. These are joinable because all the keys in here are less than any of the keys in here. So we can write a big less. Therefore, they are joinable. And the join will give us a tree that has all the keys in here. Okay? Any questions? Good. So that's it. So now we're going to solve some puzzles now to see if we can implement this interface using just split and join and nothing else. Okay, so that's our mission. Can we implement that interface using split and join? So I'm going to copy split and join up here, just so that we can use this board again. Split takes an alpha tree and a key and gives us a bool, an alpha tree cross alpha tree. And join takes 2 alpha trees and gives us a alpha tree. So what we're trying to do here is, one thing that I've learned from Haskell is that it's good to be lazy. So what we're trying to do here is we're trying to come up with a minimalist implementation. Okay, you can think of it this way, based on split and join. So we're being very lazy. What can we? We're trying to come up with a minimalist implementation in the sense that we're just going to use these 2 functions to implement all of these operations, and then we can think about implementing split and join. Okay, good. So let's implement find using these 2 operations. Okay, suppose I give you a tree and a key, and I want you to find the key in the tree. Any ideas? Split. Excellent. So all I need to do is, okay, look at split. So I'm going to split the tree using the key, and that's going to give me a left. How did I write it? is it bull crap? Oh, okay. So it's going to give me, found left, right. Okay, I'm just going to use lowercase letters for everything. So then in, we just return found. Right? It's just one liner. Okay. Let's do an insert. A key into a tree. The other way around. Okay, this is also the other way around. Sorry. KT. Okay, let's insert a key into a tree. What do we do? Good. So we want to split. Okay, let found L comma R be split TK. So now what we now have is all the stuff less than the key is in L, okay? And all the stuff greater than the key is in R. And we have an indicator whether that key is already in there or not. Okay, so how should I proceed? If found, then don't do anything, right? Good. If found, then do nothing. Else, return the tree because it's already there. Otherwise, I want to construct a new tree that contains the key. How can I do that? We want to join, but okay, good. We want to join, but we need to add the key somehow, right? So what we want to do is let's assume that we have a way of making a single tree out of a key. Okay, so I guess we need one more operation perhaps. Or do we even need that? Can't we? Yeah, we do need one more operation. So let's have, an operation called singleton key that gives me a tree consisting of a key, single key. Then I have basically these 3 trees that I want to join. And I can use join because the invariant holds. This guy is less than that guy is less than that guy. So I'm going to use a join to join these 2 up, and then I'm going to use another join to join these 3 up. So all we need is then something like this. Join, okay, L, join singleton key R. Okay? So this pattern here comes up common enough that we'll call this a function. Let's say that this is a function join M. Okay, it takes L, key, and R, and it gives us a tree that consists of these 3 things. Yeah?
Does it change the structure of the tree? So it returns 2 trees, right?
Yeah.
So once we use it in find, we don't have to change the structure of the tree.
Do you not want to? For example, if you use, that's a good question. So the question is, so far we didn't tell you what, we didn't talk about what split exactly does to the tree. Okay, it could rotate it could do some stuff, and that's okay from our perspective because we do want to abstract away from that. It does whatever it does. And we just return the tree that results. Now, it is important, though, that we let it modify the tree as needed because actually some data structures exactly do that. For example, if you use splay trees and if you do a lookup, splay tree is actually going to bubble that node up to the root. It's it's the key thing that it does. So we need to allow it to do some modifications. Okay, very good. So, in fact, then you have a good point. I think what we should do is probably replace this tree if we want to be loyal to this play tree semantics in the lookup here, in the find function. Oh no, that's okay. We're good. Okay, never mind. Except you probably want to. Let's not worry about that. Good question.
I was wondering before, might be a reason, but why we did not define the joint to be the inverse in a way of the split? Like joint takes 3 arguments, and if you assume on one tree all the keys are less than the singleton argument, and that in turn is less than all the ones.
Yeah, you can do it like that. Yeah, but then it's basically this operation, right? Yeah. But the nice thing about join is that it's even more irreducible in the sense that you can implement this in terms of join, but not necessarily the other way around, because you have to cook up keys out of thin air, right? Okay, these are good questions. More questions? Yeah. Yeah, like let's write singleton here and implement it first, right? So singleton, what does the singleton do? It basically gives me node, okay, leaf, key, leaf. Okay, that's singleton.
You want leaf to be basically null value.
I'm sorry?
So you basically just want leaf to be a null value.
Null value. What?
Doesn't do anything. Yeah,
I'm unsure what you mean by that. That's in a type setting, right? That's how we've defined the tree, right? The tree is the definition is here. So I think we do want to. I'm sure there are other ways to do it in a non-type setting, but in a type setting, I think we do want to do just do that simple operation. Question? Yeah.
Just to make things formal, since here we obsess about types, right?
Yeah.
Make sure the type of singleton is from alpha to alpha 3.
Absolutely, yeah. So that's a good point. So the type of singleton is alpha to alpha tree. Okay, excellent. Good. All right. So let's see. Where are we? We did find, insert, and then we introduced this join-m operation. So let me write join-m here as well. So as we go through our implementation, we've added new things. Join-m is alpha tree cross alpha tree, arrow alpha tree. It's syntactic sugar, right? Join-m is syntactic sugar. It's just 2 joins. Good. So we did that. Now, the next operation would be delete. I can squeeze it in here, I believe. So we're going to delete a key from a tree. How should we do it? Split and join. Exactly. Right, so we don't care about the result. We split the 2 trees, our source tree, and we're just going to join left and R. Right, because by definition we know everything in L is less than key, everything in R is greater than key, therefore they're joinable, so you just join them. Okay. So let's stop for a moment, and let's assume here that our split and join operations both take log work. They both do log work, logarithmic work. In that case, what is the cost of these? So this one will be log, because it just does a simple split. This one would be log. It does a simple split followed by 2 joins. This one would be log. It does a simple split followed by 2 joins. So we get an asymptotically efficient data structure here. Okay. Yeah?
In number of internal nodes?
In the number of total nodes. We didn't tell you how to do split and join efficiently right now, but we'll see that in the next lecture, latest. Okay, good. So let's move on to, these are all sequential, right? They're just doing one thing at a time. 19th century. So let's move on to interesting stuff, intersection, union, and difference. So let's try to do intersection, and what I'm going to do is I'm going to start it off, okay, and then let's see if you guys can complete it. Intersection, so we're going to have two trees. Let's call them T and U. Okay, our intention here, we don't have any information about we don't have any ordering constraints or anything like that. They're just two trees, and we want to find all the keys that are in both. So let's maybe draw an example here. So let's say I have, 5, 2, 4, 1, 6. That's one tree. And another tree is 9, 7, 8, 4. Let's put an 8 here as well. And then, 10, 11 or something. Okay? And when we intersect, we want to come up with a tree that contains 4 and 8. That's all. Okay, maybe we want something like this. Maybe we want something like this. Okay, any one of those would be acceptable. Okay, so how do we do this? So one way to do it would be to go over the tree and then say, well, find 5. Okay, and then find 2. And if it's there, find 6. Do it sequentially one by one, right? That would be one way to do it. It's not going to be work efficient. It's not going to be span efficient because it's doing everything sequentially. What else can we do? Maybe we can split. Yeah. You can branch. Split is good because once we split, right? So let's say that which key should we use to split? The one of these. We can take one of these. Let's say that we take this guy. Okay. Then this tree itself is very easy to split because we can generate 2 halves. This is less than, that's greater. Beautiful. So if we can somehow figure out all of the stuff that's less than 5 in this tree and all of the stuff that's greater than 5, then we can do things recursively. Huh? So that's the idea. So if we can find all the keys in here that's less than 5 and all the keys in this that's greater than 5, then we're golden because we can say, we know that we can do recursively intersect the 2 in parallel, recursively intersect the 2 on the right, and we're good. Okay. So let's write the code for that. Okay. It might be slightly subtle. Raise your hand if you have any questions, and I might be making mistakes. I'm not. I'm just kind of flying off of my head, so who knows what mistakes I'll make. Yeah.
Don't we have to check 4 intersections then? Because there's 2 subtrees on one side and 2 subtrees on the other side. You can't just assume that,
Excellent question. Good. Excellent question. So what your friend is saying is, okay, we have, let's say L1, R1 here, and then we have L2, R2 here, right? 4 trees. Let's draw them like this. Excellent question. Okay? Don't we have to check L1 intersect L2, L1 intersect R2, R1 intersect L2, R1 intersect R2? Don't we have to? Why do we not have to check?
Order. We assume that L1 intersect R2 is going to be empty because of dividing them.
Exactly. You've answered your question. Yeah, exactly. So the point here is that because we've carefully split with 5, we know that the stuff in here can't be in R2 at all. Right? On the L1 and R2 intersect is empty. So we don't have to do anything.
The R1 and L2 could easily not be. We still have to do 3 checks.
R1 and L2.
No, it's the same deal.
So, because it's already greater than the key, right? R1, all the keys in R1 is greater than our split key. And all the keys in L2 are less than the split key. So again, it's empty. So all these four combinations, the only ones that could result in non-empty is L1 and L2 and R1 and R2. Yep.
There's the H, which is both in R1 and L2.
There's what?
The H.
We're splitting on the 5. We're splitting on the same key. Yeah, we're splitting on the same key. Yeah. Yeah, sorry. Oh, let's okay, let's back up. This is very important. Good, let's back up. It's very important. I don't mean L2 is not this thing here, okay? Is not this. R2 is not this thing here. We're going to split this into L2 and R2 such that L2 contains 4. R2 contains 7, 8, 9, 10, 11.
The left split to make your right split.
Exactly.
Just go to the top.
Yeah.
Like an idiot.
Yeah. It's perfect. I mean, it's...
If we find it, then it's in the intersection.
Yeah, excellent questions. I mean, this is why sometimes like, excellent questions. This is great. Good. I'm glad we made that mistake. So that I made this mistake of not telling what L2 and R2 is, because now we know, everybody knows, right? Okay, good. So the rest is now kind of, writing simple code. So let's see if I can pull that. So case T of, I think we're going to have to like check both. So let's see. If T is empty, right, what do? We just return U. Okay? Good. Okay, not everybody's sleeping. We want to return empty, right? Yeah? Good. So if the next one is empty, then intersection, so we're going to return empty. Otherwise, we have left 1, key 1, right 1, node of this, right? So let me do a shorthand there. I'm going to write n instead of node. And then, now we know both of them are nodes, L2, K2. I don't need to pattern match on that. I'm just going to leave it as U. Okay. Okay, so now we have the next one. So what we're going to do is we're going to take key 1 and split this guy. So we're going to get let L2 flag R2 be split with key 1 U. Okay? So we split. Now we've got our L1s and R2s and all that all laid out. So now we're going to do recursive calls. Okay? So we're going to say, okay, L comma R is intersection. What am I going to intersect? L1 and L2 in parallel intersect R1 and R2. That's the magic parallelism. Okay, so now we've got the two sides. So now what do? Good, I need to check the flag. Why do I need to do that?
You need to decide if the K was in the intersection.
Absolutely, right. Is the K in the intersection? So we're going to check the flag. If flag, then. If it's been found in the other tree, then we know it needs to go to the intersection. So we're going to say join. So we want to now, we have like 3 trees in our hands, and we know how to do that. Join M, L, key 1, R, okay? Otherwise, it's not an intersection, so we just join the other two. Join L and R. Did I get it right? Is it okay? Yeah.
Just real quick, the let's syntax and semantics here. Like, what exactly is this? I'm just not sure what it's. So it's let L1, let L2, L2 flag R2, which is a triple. But it's B split, which is this.
What does split design?
It's like a multiple assignment of the split dot.
It's like
if you want to think in programming.
Oh, okay.
It's
So
like
as a binder.
Yeah, you instantiate every one of those arguments with the results of them.
Return triple.
Oh, yeah, I see it. I absolutely see it. Okay. Okay, awesome. Thank you.
No, okay. No problem, yeah.
And
I did nothing, so.
to be consistent, you flash the first one.
So
Returns full and then 3 and 3. Not
oh, I see. Okay, thank you. Okay, so I this is why I never program in an untyped language, right? I can barely keep 7 things in my head. As I said, this is my thing. And if I'm teaching, I can only keep 2 things in my head. Something, the other 5 disappear. Like, I don't know where they go, but I can only keep 2 things in my head. And if anything more than a tuple, out. No way. Okay. So, Guy and I joke a lot because after we teach, believe it or not, you guys, if you have not taught before, you might not have experienced this, but there's some effect of teaching on us that I think perhaps on everybody, but it's pretty noticeable on both of us. The hour or 2 hours after teaching, we're like, what's going on? Where am I? It's honestly like sitting on those chairs, you never would think that coming up here and teaching these things would actually drain you or anything, but it does somehow, yeah.
What do you join on in that case? Is it join M?
No, it's a join. It's just
In that case.
join M. It's a join M, yeah.
Then what's the macro for the double connect?
This join M is alpha tree, and what it does, it makes a singleton tree out of the key, and takes these 2 trees and then joins them all. Yes. Yeah.
Oh, yeah. L2 instead of L1.
Oh, here. Oh, sorry. Oh, this. Oh, yeah. So this is L2, R2. Good. Thank you. Yeah. Okay. So let's maybe this is very important. So slow down and simulate on that so we can actually see. So what's going to happen is that we're going to use 5 to split this. Okay. This tree here. Oh, I can't move that. Okay. So this is L1. Okay, let's see this in action. It's important. Okay, so this is L1. And this is R1. And this is K1. Okay, now we split. When we split on this here, we want only 4. So our L2 is this, and our R2 is this. Okay, in some shape or form. The split might have, jumbled them up, but something equivalent to that. Now we're going to recur on these 2 and those 2 in parallel. So these guys, let's assume everything works correctly. So this recursive call is going to give me 4, and this recursive call is going to give me 8. And the flag is false because it's not in here. So I'm going to join them, and join is going to just do that. Okay. Now if 5 was there, suppose that we put 5 in here, I think we would maybe do this, okay? In that case, R2 would actually have 5, what am I saying? 5, so it would be exactly the same. This guy would be exactly the same. It's going to give me again 4, but the flag is going to indicate that 5 has been found. So the results are going to be exactly the same, but flag is indicate that 5 is found, and the triple join is going to then give me this. Okay? A tree like this. Okay? Beautiful, good. So that's intersection. Now, puzzle for you. Team up with your friends, as usual, and do union. Okay?
Point out, union was the exercise I gave in yesterday. So the people who did the exercise I had stopped.
Did anyone do it? Did anyone do it?
I don't know anyone did it. The only difference is I didn't do the, instead of doing a join, I just created a node so that the output was not.
How many of you have figured it out? Oh, awesome. Who wants to come and do it on the board? You want to do it? Come.
All right, so first I guess you'll use a bit of the same code here. Erase some part of it. But in the base case, we should... different colors. Yeah, different color. Yeah. Let's do that then. So in the base case, instead of returning the leaves, we will return the tree we have here, and we're taking the union and not the intersection. So U and T. In this, we're doing past the same, well, we don't really care for the flag here, since we're not taking the intersection, we're taking the union, so we already know that K should be in the tree here. We'll do the split again. Here, we'll do some union. Union. And now we are not really doing this all the time, but we're just doing join M on, so join M, that was
Okay.
L, K, R.
Just need to change the name of the function.
Yeah, oh, yeah, as you. That would help.
Bravo. I was going to give you an award. Jack escaped so quickly. Okay. Bravo. So your friend just nailed it, I think. Any questions about how this? It's actually simpler than intersection, right? The only difference is that because we're putting the keys together, we don't need to anymore care about the flag because we're going to include K anyway. And so it's a simpler piece of code, actually. Okay. So any questions? Good. Now, what happens if I replace this with here, with that? Excellent. So I could, right? Semantically, it would be the same. In the sense that it would contain the right keys. Except it's not going to rebalance. So it's just going to take L and R, and it's going to put K there, but it's not going to give the algorithm a chance to rebalance. Yeah.
Unbalanced is still correct, though.
Exactly. Unbalanced is still correct in terms of the keys. It's still correct. It's just not going to give us the balance. And for those of you who've done the exercise that Guy posted yesterday, it was actually just this code. Right? The exercise was this, actually, the union of two trees. Yeah.
I think if we use the flag and do again the same transformation he did to the intersections of mutatis mutandis, we get the symmetric set difference. We get the elements that are in one,
Yeah.
other,
Okay,
not in both.
I think I see what you're saying. Yes, correct. Yeah.
Sure.
Yeah, because it's a different. Yeah, in that case, in one case you don't have the key. In the other case, you have the key. It's just going to be a different thing.
If you have it in both, then you don't want it in
Yeah, then you don't. Yeah, exactly. Good. So, how about difference?
Almost.
How about this operation here? Oh,
So, yeah, you'll have to change a bit. So in the first case, leaf and you, then you'll get leaf, and in the second case, you'll
get T correct.
yes.
Because that minus that, right?
And then, yeah, doing that one there again, then
Yeah.
you'll have to call difference instead of union. Your power
Yeah.
calls, and then
Yeah.
you'll have to get an if check back again on the flag.
It's like the intersection, right?
Yeah.
A little bit. Yeah.
And now we'll kind of do the reverse.
Do the reverse of what the
Use there,
intersection.
And we use the normal join, and if it's not that, then we use the join now.
Exactly. So difference, okay, we won't go through it here, but it's basically same exact format, right? Just slightly different operations that you do in various branches. Okay. Good. Excellent. So, going back, so now we pretty much completed an implementation of binary search trees, including the classic operations find, insert, delete, and the 21st century operations intersection, union, difference, all using just really split and join and a singleton function, right? Which is not really even a function. But anyway, so 3 operations. Most importantly, split and join. And there is no balancing whatsoever going on anywhere at all, except in split and join. Okay, so that's what's neat about this, is that if you have this implementation, if you're used to programming in ML, for example, you can functorize your tree with split and join, and it'll take the split and join as arguments, the functor, and then you generate this automatically for any kind of balancing scheme you want. All you need is split and join. That's all. You can just plug and play whatever implementation you want. So very elegant. Okay. Excellent. So now next question then is, let's think about a little bit about the cost of union. Okay, so now that we have wrote the code for it, and let's assume that split and join operate in log work and span, and let's reason about what should the cost of this be. I guess the question is fundamentally, okay, we've done this implementation, but is it efficient at all, right? Okay, so let's think about the work first. So let's see that assume that we have a tree with, let's say that we're doing union, and then we have N and M, 2 trees. Okay, let's assume without loss of generality, let's say M comma N. Assume without loss of generality that M is less than N. Okay, or equal to, we should say. Under that assumption, what's the work? So let's check, right? So the base cases are simple, so let's not worry about that. They're all constant. The inductive case, what we have is a split operation that does log work, and then 2 recursive calls on L1 and L2, and then a join operation that does again log work. So let's be very optimistic, and let's assume that we get perfect splits everywhere. That when we split our tree, we get a perfect split on the right tree. And furthermore, our left tree was perfectly balanced, so we divided exactly in half. So we're being very optimistic, okay? The point is that the rest of the cost is order log n, okay? So on the right. Because all we did is a split and a join. Okay. And for join, I guess we might want to include both. So let me write order log m plus n here. Okay, so that's our recursion. What does this give us? It requires a bit of work to solve this thing, but it basically will give you order m plus n. No, it won't give me order m plus n. It's going to give me okay, good. No, it's not going to give me order m plus n. It's going to give me something different. Any ideas? Okay, let's exercise our minds a little bit. So what's happening is that we've got our big tree n. Okay, and we're always dividing the big tree using keys from the right-hand side. So what this gets into is it gets divided like this, n over 2, and n over 2. And then it just continues on like that. Until when? Until we have m over these. Okay, m of these guys. And each one would be of size n over m. Okay? So what we're doing is just dividing this guy up, tuck, 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 until we run out of keys on the left tree. Okay, so we're left with, and how many keys do we have to start with? M. So assuming everything is perfectly partitioning, we've got like beautiful n over m's everywhere. Okay, m of these guys. Good. How many of these do we do? Total splits that we did like this is m, because we did exactly m splits to reach this point. Okay? To reach here, exactly the number of splits that we did is m. We basically ran through this main body of the function exactly m times. And how much work did it take to do that? Okay, log m plus n. Is that correct?
M is the size of the tree on the left.
Good. M is the size of the tree on the left. Assume without loss of generality that it's smaller. And then we have a bigger tree on the right. So what we're doing is we're taking the left, splitting into tuck, 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 right? And we get down to we divide our right tree exactly into m pieces, each of which has size n over m.
And why is the word not m log n, but log m plus
Why is the work not m log? I mean, they are the same thing because n is. Yeah, they're the same thing. You can write it like that. Yes. Yeah, you can write it like that. Yes. Yeah, it could be written as m plus n. Yeah. So this seems to be an okay upper bound, right? There is a tighter upper bound, actually. So in the sense that, so what I've written there is, I think, correct. There's a tighter upper bound which is order m log n plus m over m, okay? That is more interesting, right? And how can we establish that? It's basically saying, you can think of this as saying order m times log n over m. Okay, so that requires a bit more thinking, okay? I'm not going to get into that exactly, but the reason is informally that because you're not drilling down to this other tree, okay? You're only working on the smaller tree, but not on the larger tree fully, and that allows you to get this bound. So now what this implies is that, let's talk about the implications of this, or that bound, right? What this implies is that if n and m are approximately the same, you get order n plus m. Or like whatever, order n, right? Which is optimal. Okay, so this is very important because when they are approximately the same, it's optimal. If n is a lot larger, this means that it actually takes more like this. If m is a lot larger, okay, it's actually smaller. It's more proportional to the smaller tree times log n, because you're doing those searches in the bigger one. But the bigger one is now getting joined up much more efficiently. You don't have to drill down all the way to the leaves. Good, so that gives you basically a smaller thing than you would expect. Not linear in n, it's linear in the smaller tree. Okay, so this turns out to be, optimal. In the comparison model, you can't do any better than this in terms of the union. Okay, in terms of work, it's an optimal algorithm. Okay. Now what's the span? The span is even easier, right? Because we do the two sides in parallel. We do log span, but then we do two sides in parallel, so we get a log square n bound on the span. Log square m plus n. Okay, I believe. So it's an excellent parallel algorithm, because we are able to do the two sides in parallel, and we only do log work at each level, and there is a total of m levels, in fact, log m levels, so you get that bound. Okay? So backing up, what we've achieved is that basically all of these, essentially whatever you would want to do in terms of sets and dictionaries and binary search trees, all of these operations, inserts and deletes and finds and intersection, all of that in optimal work and very nice log square n span. It's basically fully parallel. Now to give you an intuition, like you might say, okay, does this really work in practice? There are many graduate student Yihan completed implementations of this algorithm using many different balancing techniques, and it works incredibly well in practice. Incredibly well. So It's engineering such an algorithm to work wonderfully well is not easy. In ML, it's easy, but actually, Johan did it in C, and she's actually doing very fine-tuned optimizations and comparisons to existing systems, and it works incredibly well. Okay, good. So in the next lecture, we're going to talk about how we might implement this split and join by using a specific balancing criteria. Okay, we'll see that it's actually not hard to implement split and join by using a specific balancing criteria. Okay, we'll see you soon. Thank you. Any questions? Any questions?
What about the span?
Span is log square and, yeah, because there are log m levels, and each level does log n span, so it's log m plus n, log square m plus n, mostly.
So here we are thinking that the trees get properly partitioned, like exactly
Good.
in worst case.
Oh, I see, sorry. Oh, I should have, good, I forgot to say. So in this analysis, I assume that things are perfectly balanced, right? Obviously, that's not the case. But it turns out that if they are not perfectly balanced, it only helps you. So it's an interesting artifact of the analysis is that if things are not perfectly balanced, it actually improves the work in span because you're able to take advantage of it. So this assumption is actually a pessimistic assumption, and not balancing only improves the work in span, even though it may seem counterintuitive. If you think about it, it does, because you're basically able to right, because you're able to, the advantage is that there's a slight modification to the algorithm that you have to do in order to take advantage of that, but basically you can always binary search the bigger tree, and that allows you to not pay linear in the size of the bigger tree. Yep. Okay, excellent work, guys. We'll see you soon. Yeah.